Hi, I'm Isabella Stoichev, and for my Physics 1211 Lab 1, I'm going to discuss motion on the x-axis at a constant velocity. So, to give an outline of what this lab is, the goal is to observe, predict, and explain the motion of a ball moving in the same direction without changing velocity. I will do this through both an experimental evidence and tracker shown by rolling a lacrosse ball on a kitchen counter, and then also a computational model in which conditions are perfect with Newton's second law, and I used Python to create this model. So, speaking of Newton's second law states that an object in motion will continue in motion until acted upon by external forces. This basically states that if an object is moving at a certain velocity, unless there are other forces acting upon the ball or object that aren't actually a part of the original motion, the object will remain at constant velocity. This is further shown by the momentum principle, which is force is equal to mass times acceleration, and when acceleration is equal to 0, force is also equal to 0. Overall, the results of the lab had some discrepancies, but the models produced similar results with positive relationships between the position and time and a constant velocity. Some assumptions we make with Newton's second law is that there are no external forces, the ball is moving in only one direction, no curves, just a straight line, only one dimension, and the point has a definite mass and trajectory. To begin, I will show the tracker video that demonstrates this experiment. So, as you can see, the ball is rolling in the positive x-axis direction, and it is moving at a constant velocity, as shown by the graph that demonstrates the position versus time. So, as the position and time have a linear relationship, it is obvious that the ball is moving at a constant velocity. If there was a nonlinear relationship, there may be acceleration involved, but it was at a linear relationship. Also, to discuss the axes used in this lab, I decided to put my ball on the positive x-axis. However, you could also decide that your ball would be on the negative x-axis. And so if it was moving in the negative direction, the results would be the same, however the relationship would be negative instead of positive. This would still demonstrate a positive or a constant velocity and a linear relationship between time and position. So overall, the results would be the same. It would just be a different relationship. For our computational model, I used coding in GlowScript and modified a starter code in order to make the lab fit my particular situation with the ball and with the kitchen countertop more prevalent in the code. So obviously the first thing I needed to change was the ball's mass, and the average lacrosse ball is 0.14 kilograms, so I changed the mass to 0.14. I changed the velocity to the average velocity of what I found in tracker by subtracting two y and x values, and this gave me 0.127 meters per second. I changed delta t to what the frame time was in tracker, and that was 0.003 seconds. And then I changed the time to the total time of the video, which was 1.168 seconds. Finally, I needed to update the equation for the momentum principle in Newton's second law. So what I did was I did the initial velocity plus the net forces, which would be 0, divided by the mass of the ball times the change in time. So when I run this program, it is clear that it is very similar, the relationship is very similar to that of the tracker video. As you can see, there is a linear relationship between position and time, which means that velocity remains constant. This format actually gives us a velocity graph, which demonstrates that it is in fact constant, as the line is just straight across. So, to further compare the two models, I put them together, I compared their two graphs separately, and then I put them together in a chart on Excel. As you can see, there are some discrepancies between the two results. However, what I would like to point out is that they both contribute to positive relationships, and they are both linear relationships. So this demonstrates that in both situations, the velocity is constant. To discuss why there are some discrepancies, as per Newton's second law, no net force means a constant velocity. However, there may be forces that were unaccounted for acting on the ball in the experiment. These include weight, drag and friction, normal force, and there may be more forces that we did not know about. So it is hard to predict if these forces were actually equal and if the net force was actually equal to 0. The ball's mass is also a rough estimation, and the ball may not have stayed on a straight path in one dimension. That is all for this lab report.